Hi everyone. We will now look at how we calculate these double integrals using techniques from Calculus 2. So let's get a visual for what we're doing. So we've got this region, we're trying to find the volume of it. So I'm just going to turn the sides off. And here's what we're going to do. We're going to consider a slice of that region. In this case, I took my slice to correspond to x equals 0. And this slice, I can work out the area of this red region. How can I do that? Well, this is just a region in the plane now. It's a region trapped between the axes corresponding to y and this curve up at the top, which is a curve. We'll look at it from this angle so we can just see it's a curve up at the top. And what's that curve at the top? Well, that's given by the function value where x is 0 and y is the variable. So it's a function of a single variable, f(0)y. And so we can work out the value of this area. It's just the integral of f(0), y as y goes from 0 to 2. And now what we can do is we can take this slice. You can't really see it moving, but I am moving it now. I'm moving this slice along. And for each x value, I can go ahead and compute the area. Again, it would just be the integral of f, whatever the x value is we're at, which would be a constant, and y, which is our variable. And we'd integrate that from 0 to 2. So we can find the areas of all these red regions. The area of these red regions is just dependent on x alone. So the area of these red regions is going to be a function of x. Once I know the area of each of these red regions, then I just integrate over that area function, which is a function of x. So I integrate over all of these areas, and I get the volume of the solid. So that's our idea here, is find the area of each of these red regions. That gives me a function a of x, and then I integrate the function a of x as x goes from 0 to 2. And that sweeps out the entire volume. So here's our picture for this situation. We've got, for any x value, we can work out the area of that slice. A of x is equal to the integral from c to d of the function f. X is a constant because we're fixing it for some x value. We're now finding the area of this region for that constant x value. So it's the integral of this function f at x comma y, where y is our variable. Y is allowed to change, and y ranges from c to d. So that gives us that area of this red region here. And then to find the volume, we'll put that in blue because we're finding the volume of the blue shape. What's the volume? The volume is obtained by integrating over all of these areas. And that goes from a to b. So that means the volume is the integral from a to b of the integral from c to d of f of xy dy dx. So there's our area. Maybe I should have put that in that area in a different color, but that's the idea, is that we've just substituted for that area in terms of what it is as an integral. So that's how we can compute the volume. In other words, that's how we can compute the double integral. We just do one integral with respect to one of the variables, followed by the integral with respect to the other variable. Now you may ask, can we switch the orders in which we do the integration? Could I integrate with respect to dx first in the inner integral, and then dy in the outer integral? And the answer is absolutely we can do that. We'll just look at it from this perspective. Take a slice for a given y value. Find the area of that slice. So that would be for the fixed y value, we'd be integrating f of x comma y, where y is now thought to be a constant, and we'll integrate that as x goes from a to b. So that gives us the area of this region. Now to find the volume, and that's for any given y value. So then to find the volume, we integrate over all of these slices. So we integrate over ay as y goes from c to d. And again, this gets just replaced with the integral that we have representing it. So we got the integral from c to d, the integral from a to b of f of xy dx dy. And I'll put parentheses around here. And so that says we could evaluate the integral by first evaluating the x integral and then the y integral. And that's what we have written up above. The double integral can be calculated in either of these two ways, and these are known as iterated integrals. So iterated integrals. And this is because in order to compute the double integral, you just compute the two integrals one after the other. You integrate with respect to y and then integrate with respect to x, or vice versa. You integrate with respect to x first and then you integrate with respect to y first. So you iterate through the integrals. All right, let's have a look at how we can put this into practice. Let's evaluate this double integral. So just to get a picture of this, we are integrating a paraboloid, z equals x squared plus y squared, over the interval. Now it's good to keep in mind what matches with what. So that matches with the integral. So those are our x values. So they go from -1 to 1. That's our x-axis. And what do our y values go from? They go from 2 to 4. 2 to 4. And so we are integrating over this rectangular region here. And so those are our, again, those are our y values. So y is trapped between 2 and 4, and x is trapped between -1 and 1. Okay, so that's just a little bit of the anatomy of the double integral, how to read off the various limits of integration for our variables. So how do we calculate this? Well, we can use the iterated integral technique, and that is to first focus on the innermost integral and then do the outer integral after. So we just keep the outer integral for later, deal with the innermost one. What is the innermost one? It's the integral with respect to x of x squared plus y squared. Here we're treating x as our variable of integration, so y is a constant relative to that variable, just like when we do partial differentiation. If our partial differentiation is happening with respect to x, we treat y as a constant. Same thing here. You can think of this as partial integration. You integrate with respect to x first, and then you integrate with respect to y afterwards. So this is the technique of iterated integrals. So the antiderivative would be with respect to x is 1/3 x cubed plus y squared x. That's going from -1 to 1 dy. Now we evaluate at the endpoints and take their difference. That will get rid of all the x's and just leave us in terms of y. So this would be plugging 1 in, we get 1/3 plus y squared. And then that's minus -1/3 minus y squared. So that's the inner integral. We can clean it up a little bit before we go ahead and take that y integral. So you have 1/3 plus 1/3, so that's 2/3 plus 2y squared dy. Now we can go ahead and compute the next integral with respect to y. So that's 2/3 y plus 2/3 y cubed from 2 to 4. So that would be 8/3 plus 2/3 times 4 cubed minus 4/3 plus, so 2 cubed is 8 times 2, so that's 16/3. And this works out to be 116/3. And so there we go. We've just worked out a double integral by this technique of iterated integrals, using calculus 2 techniques, doing one integral at a time. Let's have a look at another example. So here we want to integrate x sine of x plus y over this region R, which goes from 0 to pi by 6, and y goes from 0 to pi by 3. So we're over an interval 0 to pi by 6 for x, and 0 to pi by 3 for y. Okay, and we're not specified in the question which integral is first, which integral is second, so we're free to choose. So we'll do the integral with respect to x first. So integrate x first. So how does that look? So I'll just focus on that x first integral, and I won't even put the limits of integration in because I'm just looking at anti-differentiation at this point. This would be the integral we have to compute if we're doing that x first integral. I'd have to compute the antiderivative of this. And this is a by parts. We would take u to be x, because that we can differentiate. dv would be sine of x plus y. I'll move that over a bit because I'm a little too close to the edge. dx. And so by parts, we need to go du is dx, and we'd anti-differentiate the dv to get what has a derivative of sine. That would be negative cosine x plus y. So there's our by parts. That means the antiderivative is u times v in this case, so negative x cosine x plus y. And then minus the integral of v du. So the two minuses would cancel, and we'd get the integral of v du. So that would be cosine x plus y dx. And so we're not quite done yet. There's still another integral to do. So it's negative x cos x plus y, and then the antiderivative of cos x plus y, that would be sine of x plus y. So that's our first step, doing the x first integral. So that's our antiderivative. Now we'll go ahead and set up the integral and to how we're going to do the whole thing. So we are interested in integrating x sine x plus y dA. We're going to do it by doing the y integral as the second integral, the x integral as the first integral, x sine x plus y dx dy. I'll put parentheses around just to focus our attention. That first integral, that innermost one, is the x first integral, and so we've already worked out the antiderivative. That's above. We use by parts to get that. So this would be negative x cosine x plus y plus sine of x plus y. That's going to get evaluated from 0 to pi by 6, and then we have our dy integral that we're still having to compute. So now we evaluate at the endpoints. So that's 0 to pi by 3. So pi by 6 comes in. This is replacing our x variable. So that's negative pi by 6 cos of pi by 6 plus y plus sine of pi by 6 plus y minus the whole thing with 0 plugged in. So if 0 goes into the first one, that's a 0, plus 0 going into the second one, that's just a sine y. And so then we get our dy there. And so this becomes the integral from 0 to pi by 3, negative pi by 6 cos pi by 6 plus y plus sine pi by 6 plus y minus sine y dy. Okay, so we've dealt with the x first integral, evaluated it at its limits, and now we're doing the y integral. Now I need to anti-differentiate each of these. So the first one, the antiderivative of the negative cosine, so that becomes a negative sine. So that's negative pi by 6 sine pi by 6 plus y. The antiderivative of sine, that would be negative cosine pi by 6 plus y. The antiderivative of negative sine, that's plus cosine of y, and that's from 0 to pi by 3. So this becomes negative pi by 6 sine pi by 6 plus pi by 3, or that's pi by 6 plus 2 pi by 6, or 3 pi by 6, which is pi by 2. And sine of pi by 2 is 1. Next term is minus cosine pi by 6 plus pi by 3. So pi by 6 plus pi by 3 is, again, pi by 2. Cosine of pi by 2 is 0. Plus cos of pi by 3. And then we are going to take away everything we get when we plug 0 in. So minus pi by 6 sine of pi by 6, and then minus cosine of pi by 6, and then plus cosine of 0. Alright, so we got everything pretty much evaluated here. Now we just need to work out what these individual values are. So cos of pi by 3 is a half. Sine of pi by 6 is a half. Cos of pi by 6 is root 3 over 2. And cos of 0 is 1. So this all boils down to negative pi by 6 minus 0 plus a half minus pi by 6 times 1/2, or that's plus pi by 12. And then we've got a minus root 3 over 2 with an extra minus, so that's plus a root 3 over 2. And then a minus cos of 0, which is 1, so a minus 1. Which we can simplify down to negative pi by 6 plus a pi by 12. That's going to be a negative pi by 12. We get a half minus a 1, so that's minus a half. And then we have a root 3 over 2 plus a root 3 over 2. And so there is our final answer for this one. All right, let's have a look at another example. This one comes back to the motivating problem at the beginning, the paraboloid, and the integrating it over the square, 0 to 2, 0 to 2. So now we'll find the exact value using our techniques of iterated integrals. So we are interested in finding the volume, so that is the double integral from 0 to 2, 0 to 2 of 16 minus x squared minus 2y squared. dx dy or dy dx, we can do it in any order. We'll do it dx dy. So that means we're first going to integrate with respect to x at 16x minus 1/3 x cubed minus 2y squared x. That goes from 0 to 2. So that's our innermost integral. Plugging the 2 in, we get 32 minus 8/3 minus 2 times 2y squared, so that's 4y squared. And then plugging 0 in, everything becomes 0. So this is our inner integral. So we can combine these together. 32 minus 8/3, so we'll write it as an integral from 0 to 2 of 96 thirds minus 8/3, or 88/3 minus 4y squared dy. And so that becomes 88/3 y minus 4/3 y cubed from 0 to 2. So that becomes 88/3 times 2 minus 4 times 8/3, and then minus 0 plugged in for each of those. Okay, so this becomes then 2 times 88, that's 176/3, minus 4 times 8, so that's minus 32. all over 3. So that becomes 176 minus 32 is basically 174 minus 30, or 144 over 3. 144 over 3, that is 48. So there is our exact value of that volume. If you think back to how we did it with an estimate using the midpoint rule, we got a value of 49. So our estimate using 4 rectangles gave us a value of 49. Now we see the exact value is 48. So our estimate actually wasn't too bad. All right, let's go ahead and do another example. Here we want to evaluate this integral. Integral of xy squared over x squared plus 1 over the rectangle as x goes from 0 to 1 and y goes from -3 to 3. Now one thing we can notice about this, that if we write the integral out, so let's say 0 to 1, -3 to 3, x y squared, x squared plus 1, d, and so the inner one is y and the outer one is x. Doesn't matter which order I do it in, anyone's going to be fine. But the thing is, if I do that innermost integral, then I'm treating x as a constant. And I notice that it's there just as a multiple of y squared. So that means I can just bring it outside of the first integral, because I treat it like a constant anyway. So if I bring it outside of that first integral, it comes out as an x over x squared plus 1, and then the integral of the inside is that, dy. I could keep that dx on the very end here, or I could just move that over and put it here. So the key observation is, I'll make a little bit of room here, is that this integral splits. The iterated integral actually splits into a product of two integrals. And so then I can evaluate each one of these independently and just multiply their products. So what is the integral of the first one? So that would be a logarithm of absolute value x squared plus 1 with a 1/2 out front. Now you can do that using the substitution rule, so u equals the denominator x squared plus 1 and then go through that. Or you can just think to yourself, I needed an x squared plus 1 in the bottom. So if I took a logarithm of the absolute value of x squared plus 1, took its derivative, that puts an x squared plus 1 in the bottom, but then chain rule tells me that I'd have to multiply by 2x. Good, that gives me the x up top that I need, but I get an extra 2, so I'll throw a 1/2 out front to cancel that. However you want to think about it, that's a calculus 2 integral. We just worked it out in that way. Now for the other one, the antiderivative of y squared, that would be 1/3 y cubed from -3 to 3. And so that first integral becomes 1/2 log of 2 minus 1/2 log of 1. Log of 1 is 0. And that's being multiplied to 3 cubed divided by 3, or that's 3 squared, that's 9. And then minus 9, so that's plus another 9. In other words, it's 18. 18 times 1/2 log 2 is 9 log 2. And so there is our final answer. It's not so much about the final answer in this case. What this example is really about is the fact that this integral split. Why did it split? Well, we're integrating over a rectangle, and our integrand splits. It is a function of x times a function of y. So I observe that here because I just noticed it's a function of x multiplied by the y squared function, or the function of y. And because of that, we can split it into two pieces, the integral involving the x and the integral involving y. This is sometimes a nice observation to make when you're working with these multiple integrals, because you can start to split things apart and deal with them as just an integral of a function of a single variable. All right, that's it for this section. Thanks for watching.